thanks for coming. And it's a pleasure to be here. I'd like to thank the organizers for having me. And I'll tell you about our recent work using machine learning for oh, shit. Sorry. I tried to. No?
This is the wrong talk.
Not
Oh,
my
you
talk.
closed it.
I closed it?
Okay.
I'm trying. Yeah, okay. Sorry. Yeah, that works, right? Yeah. Great. So we use classical machine learning models to model quantum properties of matter. And particular chemistry is an interesting field because it's dictated by the physics of the valence electrons, which are quantum objects. And so the equations you need to solve are quantum mechanical equations, and we try to use machine learning to do that. Now, before I get to that, I should acknowledge the people doing the work. So these are recent pictures from my group. We are part of the University of Basel. It's the oldest university in Switzerland, 1400 something or so. It was founded, and that's the Faculty of Science here. We received a lot of funding partially for that work, and so we are really thrilled to see this interest, including communities which are foreign to chemistry. And so I feel a little bit like a foreigner here, and I think what I'll try to do is to portray the kind of problems we have in chemistry, and to maybe or hopefully convince you that this might be of interest also to look if some of your expertise could help with the problems we have. And the problems are quite substantial. Now, why would you even bother about chemistry? I picked two examples. One is more philosophical. This is Friedrich Wöhler, a 19th century chemist from Germany. He demonstrated that the atoms in an inorganic solid like this ammonia cyanide, aka the mother-in-law's, the salt for the mother-in-law, that these atoms can be transformed into urea, an organic compound which you would find in organisms. So this transition that atoms, I don't know, from Cleopatra also happen to be in your body, or from some inorganic matter. There's a fundamental sort of magical or alchemical twist, and that's certainly fascinating. Now, more from a utilitarian point of view, you could argue that chemistry is just important for human mankind. And at the end of last century, Nature published this Millennium essay, which started out by asking, what's the most important invention of the 20th century? And it wasn't aeroplanes, nuclear energy, or quantum mechanics. It was the synthesis of ammonia, which the author picked. And the reason is, if you look at the production of ammonia, shown here in green, it's a function of time. This was crucial to be produced at the industrial scale using the Haber-Bosch. I could give a chalk talk. All right, I'm not advancing fast enough. So anyhow, at the same time, so ammonia is necessary for producing fertilizers, and this allowed to avoid starvation for millions of people, and so the world population grew a lot, and if you like humans, that's a good thing. I think it's interesting, the world wars, you don't even see them on this growth, right? So chemistry is more important than politics, you could argue. So how do we do on chemistry, in terms of chemistry? How is our understanding? Depends a little bit how you define understanding, but if you just look at how well do we do in predicting chemical behavior, this is the phase diagram of water. So it shows you as a function of temperature and pressure in which aggregation state the matter occurs, and these lines show you the transitions, the phase transition lines. And you see in blue, this is experiment, and in black is state-of-the-art theory. So that's state-of-the-art, and at best you're off by 10 degrees. So if you have 10 degrees too much in your body, you're dead, right? So and this is water. It's a molecule with just 3 atoms. It shouldn't be complicated, and it's not an infrequent molecule, and it's not an unimportant molecule. So also, if you could find some catalyst, I showed the ammonia example, that was a catalyst. If you found a catalyst that splits water efficiently using sunlight, for instance, and cheaply, meaning being made of abundant materials, you would have solved the energy problem, if you wish. And so just in last year, a paper was published proposing this catalyst with iron, which is very cheap, and some simple organic ligand. And unfortunately, it's not very efficient, but it illustrates that there could be fantastic catalysts out there that just do what we need. We just don't know them, right? Because we are too ignorant. Now, why do I present this talk on a projection? Why don't we have screens all around printed on the walls using organic materials that emit light? Why don't we? Right? These are chemical questions. Now, the problem is we suck at controlling this, right? The way we do chemistry right now is trial and error. We are walking around. Of course, every now and then, even a blind squirrel will find a nut, right? So then you find penicillin and you are happy until all bacteria have become resistant. So what do, right? Now, why is it so bad? I think there are multiple reasons for this. One of them is this one, so chemical space is really gigantic. This aspirin, it just has 13 atoms. It's really crucial. In my life, I don't know how about your life, but so I just had this martini lunch, so it's quite important. Anyhow, so if you look at the number of possible molecules you could make as a function of size, and so aspirin, if you don't count hydrogens, it has 13 atoms. And you see these are organic molecules, and this is a very conservative lower bound of what's possible. And aspirin is really a small molecule, and yet it's 1 out of a billion. Right? So it's a huge space. And why is this so large? It's a convolution of two components. One is the stoichiometry. If you look at the number of elementary particles that make up chemistry, this is protons or electrons. And you look at the possible stoichiometries you could make, these are integer partitions, you see that this number increases exponentially. And so you very rapidly have very many possible stoichiometries. Now, this is protons, any single atom. The zirconium atom has 40 protons. It's roughly halfway in your periodic table, right? You have roughly 100 different elements. So you should go up to 100 if you wanted to cover all the entire periodic table. So just 10 protons give you the stoichiometries, for instance, of all these common small molecules. Now, that doesn't encode structure yet. It's just composition, right? So you add structure on that, and you all know that just take carbon, you can make diamonds, graphite or charcoal or nanomaterials. That's the only difference is structure. There's no compositional degree of freedom. It's all carbon. So you combine the two, and that's sort of the situation. And so there's an estimate. 2004, there was a special issue in Nature on chemical space. The estimate was more than 10 to the 60 possible molecules which you could make, and these are just organic molecules, so a very small fraction of the periodic table, right? And that's a huge number. So this is on the order of atoms in the universe. So people say you could not. We don't have enough atoms in the universe to make the hard drive to store the list of all the possible molecules. Not speaking of synthesizing or characterizing them. Now, in terms of our understanding of chemistry, things are like this: that these, as a function of accuracy, in terms of predicting energies, which dictate the behavior of atoms, you can only consider a certain amount of atoms, a certain scale in terms of number of atoms, or sampling them for a certain length of time. And so these are the different scales you have to consider as you go up to something that would come close to macroscopic experience, so what you would perceive as a chemical, as a human. Now, we are working, our methods live on, so given a certain budget, CPU budget, you can travel up and down on this diagonal. And so with quantum machine learning, we would like to go to very large systems at very high accuracy, so move on this horizontal. A different plot that illustrates our landscape we are navigating on a daily basis negotiates cost, computational cost, versus accuracy of your prediction. So these are typical acronyms of standard methods like force fields, semi-empirical, quantum chemistry methods, mean field theories, Hartree-Fock and DFT, this perturbation theory. Here you have quantum Monte Carlo or coupled cluster methods. They all approach the exact solution to Schrödinger's equation for any given chemical. So typically, with a constant CPU budget, you would move on a diagonal which goes like this, right? Orthogonal to that one. Now, just to give you an idea in terms of actual numbers, these are ballpark numbers. You would spend CPU years for something like aspirin to get to 1 kcal per mole accuracy, which is typically in thermochemistry, this is the experimental uncertainty. In spectroscopy, you can reach this sort of accuracy, so then you're talking decades. Now, we are trying to get here with machine learning, and we have reasons to believe that this is possible, but all we can show is really just the beginning. I'm not saying we did this actually. For some cases, we have strong indications and numerical evidence that it's possible. For that, we use the database we generated a couple of years back. We calculated for 134,000 molecules DFT numbers, so from here. So by the way, if your mean field theory, DFT is also mean field theory, if it's above this average, right, it's a sweet spot. It gives you more than you're supposed to get in terms of accuracy, then you get a Nobel Prize. So we have this database, and 134,000 molecules is it sounds like a lot. It goes up to 9 atoms, not counting hydrogens, and the most frequent stoichiometry are these sort of molecules. 7 carbon atoms, 2 oxygens, and 10 hydrogens. Now, if you arrange them in ascending order of the energy. It looks like this, and you see here in this zoom in, we have 1 kcal/mole accuracy, 1 kcal/mole window. So this is the experimental, the chemical accuracy, and within this window you see over 100 molecules, and this is zoom in on 7 of them, and you see the structural diversity of these molecules, right? So this pushes us to, I mean, this is a statement a chemist made, that enumeration surpasses the human imagination, and I hope that this illustrates that. This is also the same set of molecules, these 6,000 molecules. The color corresponds to the energy, and these are moments of inertia axis here. So all the 3D molecules are in this corner, the linear ones here, and the planar ones here. So you see this is how they're distributed. Now there's an interesting thing you see here. It's much more sparse, and there's no reason in terms of energy for this region to be sparse. Actually, energetically you should expect much more molecules here, but we do have an inherent human bias as to how we perceive chemistry. Typically we draw these 2D figures, and so when we generate with human-made rules, when we generate molecules, they often are inherently biased. So that's how this came about. Now, before I show you results here, I'd like to point out an interesting thing, that ordinarily when in physical chemistry we talk about fitting, this question comes up: how do you avoid the overfitting regime, and how do you make sure that you're in this optimum of test error versus training error? And in fact, what we really want is something slightly different. We don't actually need this kind of red regression here. Rather, we actually want to go through every data point, because every data point is a solution to Schrödinger's equation, which we obtained with a numerical noise many orders of magnitude smaller than the variance of the property we are calculating. So for all intents and purposes, our noise is negligible, and so we have the problem rather of interpolation than real regression. So this has a severe effect on how these learning curves look like. Our training errors are typically very close to zero. We actually use this to detect bugs in the code. It's a typical test you do, and then your test error must come down systematically. This was shown by Vapnik already in the 90s, that this has to be the case. And so if your test error doesn't come down, I would argue you're not doing machine learning, because you stop to learn, right? And then it's something else. You just have a model. So it was shown by Vapnik and others, and Müller in the 90s, that your error decays inversely with training set size, the prediction error. And what we do in particular is to use kernel-rich regression methods. So we estimate a new materials out of sample property. We estimate as a linear combination in your training, where you have these kernel functions, and the regression coefficients you obtain is a solution to the least square, the regularized least square problem. But our noise is practically zero. So I omitted the noise term here. So we just invert this training kernel matrix. And if you plot then the prediction error as a function of training set size, it should obey this inverse relationship. And so on a log-log plot, this is a linear one where the slope b is the exponent here. And so this is something you should really find for your model unless there's some problem. And this is a typical problem that can occur, that your machine learning model actually gives you a better error for a small data set, but then it levels off, and you don't have learning anymore. And that's something, as quantum chemists, we don't like that. So we want something that continues to converge down to arbitrary accuracy. So this can happen if, for instance, your representation is not unique. I'm showing here two examples. There's a planar geometry, for instance, of ammonia. Imagine the nitrogen in the center, and then you have these interatomic distances, S and L. And if you construct a pyramid where S and L, where S represents the edges in the plane, and L the edges of the nitrogen atom being above or behind the plane, you can arrange for geometries where L and S in these two cases are exactly the same. And if then you have a two-body representation which only accounts for distances, you couldn't distinguish these two geometries. So they really only differ due to many-body effects. And you see this, these three curves, they illustrate this. If you only have two body, you get for both geometries the dashed. If you add three body terms, this spurious degeneracy gets lifted, and you get the dashed solid line here and the solid line. And then you can distinguish them. So if you used only two body terms in your kernel-ridge regression, your learning curve looks like this. Another thing you'd like to have is, of course, a very smaller offset. So this is interesting to us, and we investigated what affects the offset. And here's an example of ethanol, and the question how you represent it can really affect how quickly your learning curves change. And there's a paper we recently published with collaborators from Google where we demonstrated that for these organic molecules you can reach chemical accuracy. And the best model here is a kernel-ridge regression model. Other colors and symbols correspond to neural networks and other representations. We did this for many quantum properties. This is just the energy. And the question then is, of course, what determines the offset of these various learning curves? So we did a little exercise where we asked, okay, what kind of functions could we use as a representation in our kernel? And we arrived at this sort of experiment where we said, okay, suppose you have a representation where you account for all interatomic distances with this Coulomb term. So it's nuclear charges of atom I and J divided by the distance. But now we have this exponent n. And in the Coulomb's law, n equals 1. If you make n equals -1, it means that this term grows with the distance of the atoms, right? So that will be unphysical, right? So if this interaction grows with the distance. And so if you have 1, your learning curve is here. If you become unphysical, you're here. If your interaction grows quadratically, it's even worse, and your learning curve goes up even more. So in other words, the more physical your representation, the lower your learning curves, the more it resembles the energy of your target. And so we then decided, okay, let's put a force field as a representation, and we can have force fields that account for atoms, bonds, angles, and torsional degrees of freedom. So these are 2-body, 3-body, 4-body effects in your system. If you provide them in the representation, your learning curves come down from black to red and blue. These two are just from the literature. And this works for all sorts of properties. Here we have other electronic structure properties which are in the data. And you can also see for the outliers that as you go from the dressed atom to the bonding terms to the angle to the torsion, the error on the outlier systematically decreases. So on the left hand you have 9 properties for these isomers, these C7O2 molecules, and here on the right hand side you now have learning curves for the 134,000 molecules, and we always observe the same trend that as you increase the degree to which your representation is realistic, your learning curve comes down systematically. Now, these are the latest results, and you see that for something like in between 1,000 and 10,000 molecules or so, you reach chemical accuracy for this large QM9 data set. So another question is if we can affect also the slope of these learning curves. The slope has to do with the dimensionality, and here's a spoiler that we succeeded in getting to do this. And the way we did this was by asking this question: if we can look at each atom in a query molecule separately, right? And we say, okay, let's look at this atom. Let's just account for its environment. This atom in this molecule, and we can increase this environment systematically by including in the periodic table. We extend the periodic table by the environment. So we add neighbors, 2 neighbors, 3 neighbors, and so on and so forth. And so we can have an extended periodic table of chemistries, which accounts for atoms in the molecule. And if you then look at the kernel-ridge regression model, it sums over your training instances. These are your regression weights. And then you have a double summation over atoms and molecules for J being in your query and I being in your training instance. Now you can pull the J summation in front of this, and then you have these terms for each atom J in your query. So you have a sum over atomic contributions in your query molecule. Furthermore, the number of atoms J in your query can be much larger than the number of atoms I in your training molecule. So you can have very small molecules to which you compare this atom and its environment independent of all the rest, and you do that for every atom in your query separately, right? And so you can ask this question, okay, suppose this atom here is similar to water, then I can grow this, and then it's methanol, and you see I can add more and more neighbors. This is ethanol, then I have propanol, etc., etc. And once I'm done with this oxygen, I move to the next atom in the query molecule, and I repeat. And so then I learn the local regions independently, and I train on this training set. I train this before I'm doing my query prediction. So it's like training on the fly. In comparison to a DFT calculation, which takes easily 1 CPU hour for the entire molecule, training this on the fly is negligible. So how do we know these fragments here? It's a simple procedure we have here. It's a flowchart where you go through every atom and you do a subgraph matching procedure where you identify fragments. And for this query molecule, these are the fragments you would find as you go to larger and larger fragments. And up to 7, you have something like 40 different fragments. And if you remember before, I mentioned 1,000 to 10,000 training instances. Now you have 40, right? So this is the number of fragments here. This is the error on the energy you make for predicting this molecule. And this is the size of the fragments you need. So once you go up to 7, you're here, or 40 molecules. And in black, you see the error. And the error comes from above. It crosses 0, it becomes negative, and then it comes up again. As your fragments grow, you approach the energy of your molecule. It becomes more similar. So you come down, you gain by the delocalization of the electrons. But as your fragments become even larger, the query molecule actually contains some strain. It's not as relaxed as small fragments. So the fragments will actually be lower in energy than your query. And only once the fragments become large enough again to include this strain you have, for instance, this 5-membered ring here, you come up again from below. So we can understand these kind of error curves. In red, you see a different property than the energy, namely the polarizability. this doesn't only work for the energy, also other properties can be modeled this way. Now, this was just one query molecule. We can do this for our data set. So these are average prediction errors made for 11,000 molecules out of the 134,000. And this is how that error comes down, and at 10 to the 0 you have chemical accuracy. And this is from our paper with the Google collaboration. This is chemical accuracy in these units in electron volt. I'm sorry, this kcalpamole is roughly a factor of 20 in between these two. And you see you hit chemical accuracy at 30,000, right? And here you're at something like, what is this, 50. So we can change this slope by encoding for a different dimensionality in that. And so we compared this also to taking random fragments. If you take the random fragments rather than selecting them by the graph, the subgraph matching, you get this kind of learning curve, which has this sort of slope. You can, since these fragments are, they repeat throughout the molecule, but also throughout different query molecules, it's like a dictionary of small fragments of chemistry. It's like the DNA of chemistry, right? So it's a very finite set of chemistries you actually have to account for. And if you compare it to the total size of chemical space, which is 10 to the 60 or so, that the number of possible fragments that actually occur is quite small. And so we looked at the frequency distribution of these fragments, and that's shown here in black. So the smallest fragments are obviously the most frequent ones. And as you have larger and larger fragments, the less frequent they are in your average query molecule. And if you go up to 7, these are the least frequent examples with 7 atoms. And you see they are highly specific for certain query molecules, for certain chemistries. So this is very similar to the frequency, for instance, of words in sentences, right? So what we have is something like the analog to a dictionary. So it's a dictionary of chemistry, if you wish. And then your sentences are the query molecules. So since these fragments are being shared among different query molecules, we can look at overlap. So these are 3 different query molecules, and they share, here in the overlapping region, they share fragments, and the extent of this overlap also tells you how similar these 2 molecules are, and it also gives you a measure in terms of energy, because these energy contributions are always the same no matter what's your query compound. Now, let me correct that. They are the reference values for these overlapping molecules are the same, but they enter in the kernel regression different training sets, right? So it's a subset that's identical, but because the overall set is not the same, their regression coefficients will actually differ. Now, because it's an atomic summation we can print out atomic energy contributions. And you see those here in numbers next to the atoms. And what you see in brackets, these are numbers that you would obtain from a physics-based force field estimates. And so the numbers in brackets are numbers which were derived from the physical arguments from humans. And you see, ballpark-wise, it's very similar on the scale. So your hydrogens are typically around 50 or 60 or so. Your carbons are 150 or 160. The oxygen is 90 to 100. The nitrogen is 125 or so. So ballpark-wise, the machine discovered that these are energies which are physically meaningful. Now, because this is fragment-based, it scales. So we can make predictions for very large molecules with what we think is chemical accuracy. And if you remember the plot where I showed accuracy versus size, there's a relationship in the traditional and the deductive models we have. but because we have something scalable, we don't suffer from that. So we can predict very large molecules, such as LSD here, or cholesterol, or Viagra, or Taxol, which is an anti-cancer drug. These are very complex molecules, and what you see here is many different machine learning predictions versus reference validation numbers. So all these predictions were trained on these small fragments, right? And we are making predictions for large molecules. So chemically, this is extrapolation, if you wish. But from the machine learning point of view, these chemicals are redundant. So machine learning-wise, it's an interpolation. What you see in brackets here is the average error made over all these molecules. So if you just have one atom in your fragment, you basically don't have bonds, so you're really off. Now, if you allow for bonds, your error is, this is the kind of error you would make if you were just counting the bonds. So only two-body interactions. If you allow for three-body, you get this down, and this is a typical force field sort of accuracy. With DFT, you would get this kind of error, and this is the experimental uncertainty. So this chemical accuracy reach on average with fragments up to 7 atoms. Now this also works for polymers. Here you see very large polymers, and here you see the number of monomers we tested, and you see systematic improvement. The prediction error decays systematically with system size at 100 fragments or so. You typically reach chemical accuracy. So this sort of problem we can definitely solve. These are water clusters. This is what you have to get right, for instance, to get the phase diagram for water right. Also here you see systematic improvement down to chemical accuracy for predicting these water clusters. This also works in periodic boundary conditions. These are 2D sheets of materials doped with carbon or gold. And also here you see systematic improvement, so reducing prediction errors with training set size. And here's a bulk example. This is silicon. You see the error on predicting the energy of silicon decaying, and the fragments we use here are these silanes, which are saturated with hydrogens. It's sort of the DNA of chemistry, so of course we wanted to look if we can use that to make predictions on DNA, and that's what you see here, the Watson-Crick base pair of guanine and cytosine. This is its energy, and these are the fragments you need for guanine. These are the fragments you need for cytosine, and these fragments the two share. And these down here are all the fragments you need to cover the hydrogen bonding in this DNA base pair. So with this, I come to my concluding remarks. There's one analogy to quantum mechanics. If you solved by variation principle or with quantum Monte Carlo, you solved the Schrödinger equation, you get the expectation value, say, of your energy. You have the wave function, and then you can use that wave function to calculate expectation values for any other operator to get any other observable, right? So the wave function doesn't really depend on your property. Now, there's some analogy to the kernel-ridge regression, because here when you train your kernel, the kernel inversion doesn't depend on your property. You can multiply in any reference vector to get the corresponding regression coefficient. So in some sense, the regression coefficients correspond to your property, the kernel to your wave function. We showed this for molecules. These are very different properties of many molecules, and this really works. When traditionally we map composition and coordinates to energy by solving the wave function problem, as described by my previous speaker, the machine learning really allows us to infer that solution given sufficient training set sizes. So in some sense, the traditional relationship between experiment and quantum mechanics informing the human is augmented by a third component here, where we also use machine learning to accelerate our understanding of chemical problems. This is an outlook. We used our model to predict forces now, and these are forces on a molecule which was not part of training, again using this fragment approach. And before you see the deviation in geometry, and you can relax the geometry and you obtain very good agreement. This also works for non-covalent bonding. Finally, I leave this in case you're looking for a PhD in chemistry or postdoc position. Don't hesitate to contact me. Thank you for your attention.
So I think we have time for one question. Or no question? Okay. Well, if there are no questions, we'll thank Anatoly again.
Thank you.